Hey everyone, it's Ross. So here's that quick little lesson I promised earlier. So let's talk about standing waves. Let's also make sure we understand what a wave is. So a wave is a propagating or traveling disturbance. Disturbance through a media. Now, that's pretty bare bones, right? But I mean, it gets the big picture across. You have a traveling disturbance in a media. So you kind of need all of those. Okay, so harmonic waves or simple look like this. So you typically have a starting point, make sure I got these. Okay. So usually the harmonic waveform looks something like this. So this is the pattern that repeats. Now, the thing to note here, it's pretty important you note this, is one, this is the media, right? So you're seeing this disturbance, and so it doesn't always have to start at the middle like this, but oftentimes we take a snapshot when it does. So what you first need to know is that if this is a length, and then this is actually a wavelength, but oftentimes we just say, here's a wavelength, and we give it this Greek symbol lambda. The next thing we do is we denote an amplitude. So we say the distance from the midpoint to a crest, or the midpoint to a trough, is the amplitude A. And so this is the wave pattern, or the wave front, or wave form, whichever one you want to call it. And the how long this takes is called the period. So just like before, right, we use a capital T for period, just what we do. And so it turns out like the frequency for how often this repeats is based on that period. And so there's a couple interesting parameters. Okay, so in general, for waves, so there's usually a wave speed, and so we usually say VW or V omega. It's a W for wave. And so we say it's equal to, what is it equal to? So it turns out, in general, there's a couple different ways to do it, but typically we write the equation. We say the wave speed is equal to the frequency times the wavelength. So here F equals frequency, and it's 1 divided by the period. So once again, frequency is like how many cycles do you get in a certain time frame. So it's 1 cycle per the time. So this is pretty much always true. Like let's say almost, just to cover up bases. Almost always true that the wave speed equals frequency times lambda. Okay, so that's pretty cool, right? So let's go back. So you have waves are this propagating or traveling disturbance. Whenever you look at sort of a profile, you'll typically see, something get disturbed, get pushed up and then down. So this is usually the pattern you see. and you think about how many of them you see in a certain amount of time. So that's, and then, okay, so how fast does it move down? So let's go back. Let's say, the wave speed, right? So that's all pretty good, right? Like, okay, you can count how many periods you see. You can measure the wave speed. You can either solve for frequency or wavelength. You can do all these things. But so let's sort of think a little bit less general. So let's think about string instruments. So I like to, play music. I play guitar. I don't really play a little bit of piano. I just know how to play a couple things on the piano. So when you see a guitar or a piano, you have you have each string is fixed at both ends. So that's a key detail. So let's put a little bullet point on it. Okay, what's a couple other things? Guitar is usually a fret. So let's just talk about that since I know a little bit more. Guitar frets indicate a, let's say, region where you can change the effective length of the string. And whenever you push on a fret, you change the frequency or the pitch, let's say frequency of the note that's played. So, changing from open to a closed fret is sort of the language changes the frequency, regardless of how strong you pluck. So, okay, so that looks pretty good. Okay, so we have a string, it's fixed at both ends. So these are called nodes. So nodes, pretty much, you can just say points with no motion. So the 3 means defined as. Okay, so the interesting thing about these standing waves. So a standing wave, and usually you only see this when you have 2 fixed points. A standing wave is whenever you either see just a single thing. Sometimes it just looks like, one big wave. Or sometimes you see a standing wave like this. So the wave appears to not be moving. That's how we say it. Appears to not move. So typically you'll see the wave front go, down in front, but with a standing wave, all you do is see just either one high or a high and a low, and so it just sort of depends. So that's pretty much just the basis of a standing wave. I've uploaded those videos on Blackboard in this folder to help you. But the biggest thing is that when you fix the length on the nodes, you'll get certain standing waves that can show up based on that length between them. And so this length here is called L. So fixed length L. Okay, so So just a quick recap. Let's go back to the beginning. Standing waves are a special kind of wave where they don't seem to be moving. A wave, any wave, is a propagation or traveling disturbance through a media. It could be a string, it could be water, it could be air, whatever. Harmonic waves, or simple waves, which usually we establish or express every wave in terms of like a combination of these, is just sort of a high to low pattern. Usually it travels. You have a wavelength, so where you see the full waveform. The period is the time over which that occurs. The amplitude is the distance from the midpoint to the crest or midpoint to a trough. And we're really interested in how and why these patterns repeat. So there's a wave speed. It depends on the frequency and the wavelength, always. And then you can relate it to what else it should be equal to depending on the type of wave, the type of media. And so for the waves, involved, the standing waves involved with the videos you're going to watch, you have, you could think about it as like, this is pretty much the simplest way to explain what a guitar and a piano does. Like physically why they work the way they work. At least the strings themselves. The rest of it, you have to talk a little bit more about sound. So a string is fixed at both ends. In a piano, you don't change the length. On a guitar, you push the fret and then you change the length. So we'll talk a little bit more about guitars because we want to be interested in that length change by choosing to push somewhere or hold somewhere in place. And we notice changes in frequencies when you play guitar, but for standing waves, you sort of think about the change in frequency to cause that standing wave. So once again, you'll have a fixed length. Nodes are places that don't move. And so typically, this is the thing I should have written earlier. The wave doesn't appear to move, and you count how many nodes there are. So here there's 2 nodes, and here there's 3 nodes. And there's half a wave, and here there's a full wave. So something interesting to think about. Okay, watch those videos, please. And I'm going to be uploading the lab manual shortly, so please make sure you give that a look. I'm going to be available during regular lab hours, at least the first hour for all lab sessions, and my regular tutoring hours this week via Zoom. So make sure you look for that link on Blackboard. All right, see you later. Bye.